Today I'm going to talk about a generalized impedance converter and this is a topology that gives you the ability to create frequency dependent resistors, positive as well as negative ones, and we will see that later. And we can also do some other interesting stuff. We're going to use the following network. This network has two ideal amplifiers, and one of the properties of an ideal amplifier is that the voltage between E plus and E minus over here equals 0 in an ideal amplifier. Okay, so that means that the voltage between V3 and V5 equals 0, and also the voltage between U and V3 is also 0. Okay, so keep that in mind when we go analyze what this thing does. We're interested in creating an expression for Zin, so the impedance looking inside from here. What is that? Okay, and in order to derive that, we're going to do the following. So we start with I0 over here. We're going to calculate that, and that's V5 over C5. Okay, that's the current through this Z5 is nothing more than V5 over Z5, and since V5 is the same as U, it's also the same as U over C5. Why is it U? Because the voltage difference between these 2 points, as I stated before, is 0, and the voltage difference between these 2 points is also 0. So you have U here, you have U here, and you have U here. Okay? So next let's determine what V4 is. V4 is nothing more than U, which we already said was equal to V5, plus a ratio of C4 over C5 times U. Why can you use the ratio? You can do that because the current here through C4 is the same as the current through C5. And if that's the case, you can just take a look at the ratio. The current here is 0. Okay? So you can just take a look at the ratio and you get V4 equals U, which is this U, plus the voltage differential over these two pieces, which is C4 over C5 times U. Okay? So now let's take a look at what V2 is. V2 is again U, which is the same as V3 as we said before, because V5 is U. There's no voltage difference here, so V3 is also U. So that's U here, plus U minus V4, okay, U minus V4 over C3, that's the current through C3 and also the current through C2 as a consequence, okay, times Z2, and that gives you the voltage over Z2. So this is the voltage over Z2 here. You add in U, because that's the voltage on V3 with respect to the ground, and you get V2 equals U plus U minus V4 over C3 times C2. Okay, and then as a last equation, we're going to calculate what the current here is, and you need that current to give you the ability to calculate Zin. So the current I here is U minus V2 over Z1, okay, Ohm's law, and that gives you I. So now you can divide out U over I. You can solve those four equations. Those are just four linear equations with four unknowns. You can solve them and you get this expression. So for your input resistance, or input impedance in this case, that is equal to Z1, C3, C5, C1, C3 and C5 over C2 and C4. And that combination gives you an interesting opportunity to do some cute things. For instance, we have an ability to make a capacitor using an inductor. How do you do that? Well, you want to create a capacitor which is 1 over j omega c. So what you did here is you stated that Z in is the capacitor is 1 over j omega c. Okay, and that is now equal to the definition of Z in, which is this. And now we can make a choice on what we're going to do. So if we say, okay, we need to get a j omega in the bottom, so we can use an inductor on, for instance, Z4. We could have also done it on C2, but I chose to go with C4. Make an inductor there with j omega L4 and choose all the other ones to be just resistors. Okay, so you have an R1, R3, R5 over R2 j omega L4. And if you compare that to your generic form of a capacitor transfer function, you see that C needs to be equal to R2L4 divided by R1, R3, R5. So now you have an ability, right? If you only have inductors available, you can essentially make a capacitor using this active network topology, this GIC topology. Okay? We can also go the other way around. We can also say, okay, I'm going to make an inductor using a capacitor. Okay, the result is an inductor. You have your same structure here. You choose again for Z4, we choose a capacitor here. 1 over j omega C4. Now you're going to multiply top and bottom with j omega. And as a or j omega C4. And as a consequence, you get j omega R1, R3, R5 times C4 divided by R2. Okay? And that gives you an inductor L with a size of R1, R3, R5, C4 over R2. So now we made an inductor using a capacitor. More interestingly, we can also create resistors that are frequency dependent. And you can make two types. You can make a resistor that is negative, so you can create a negative resistor. Or you can create a positive resistor, which we will do later on. The negative resistor we're going to pick because you need to find a minus sign somewhere. And as you know, a resistor is not a complex type of device, right? So there's no j omega there. So you need to get rid of your j's somehow. And you can do that by using two j's, right? So you need two type of elements, and I chose to go with two inductors. You can also use two capacitors in the bottom, of course. You can do that too, you get a similar type of result. But I chose to go with two inductors at the top. So I chose to go with L1, so this one and this one to go with inductors. And the rest are resistors in the network at that point. And if you do that, you can work it out and you get minus omega squared L1, L3, R5 over R2, R4. So now you have a resistor that is negative for all frequencies, right? And it has the following dependency with respect to omega. There's a squared there, so it's an omega squared type of dependency. Now you can use that, for instance, if you have an oscillator circuit, right, with L, that always has a small internal resistance. So this is the internal resistance from the inductor over here, right? So that gives you some sort of oscillatory behavior, right? Now what you can do is you can make the quality factor of this circuit, this oscillator circuit, better by removing this Ry using a negative resistor, right? So if you can insert a minus Ri there, which of course is dependent on omega, you can, at its natural oscillation frequency, you can make a much better filter. So that's one of the uses of this particular negative resistor approach. Okay? And as a last example, we can also make a positive resistor that is again dependent on omega. And in order to do that, you need to get rid of all the j's and also the minus sign. So you need 4 j's. Now luckily we have 5 devices, so we can actually do it. So the first top 3 we're going to insert inductors. So for L1, L3 and L5 we have inductors 1, 3 and 5. These, and there is a capacitor at C2 over here. And then there's one resistor here. If you do that, you get an omega to the power of 4 times L1, L3, L5, C2 divided by R4. And that gives you a frequency dependent resistor that is dependent on the frequency in a 4th order type of way. Okay? So that's, to me, a very interesting result also. These type of filters are used a lot in filter type of theory, these networks. These topologies are used everywhere, right? In semiconductors nowadays. Okay, I think this is a great place to stop. If you like this video, please subscribe and please like, and I'll see you in the next one.